Sirius is the brightest star in Earth's night sky. That is a simple fact, and it has been true for a very long time, not just for centuries, not just for thousands of years. For roughly the last 200,000 years, every human being who has ever looked up on a clear night has lived under the same brightest star. And for about 200,000 more years into the future, that will still be the case. The star sits in a constellation called Canis Major. That name is Latin, and it means the greater dog. Because of that, Sirius has a nickname that has stuck with it for a very long time. People call it the dog star. The name Sirius itself is older than Latin. It comes from an ancient Greek word, Sirios, which meant something like glowing or scorching. The Greeks noticed that this star appeared at a particular time of year, during the hottest weeks of summer, and they assumed it had something to do with the heat. That connection between Sirius and summer heat is where the phrase "dog days of summer" originally came from. The Romans used a similar expression, and people still use it now, thousands of years later, even though most of them have no idea it refers to a specific star. Sirius is bright enough that the only things in the night sky that regularly outshine it are objects much closer to us. The Moon, obviously, Venus, which is a planet in our own solar system, Jupiter, another planet, much larger but also much closer than any star. Occasionally Mars or Mercury can appear brighter than Sirius, depending on where they are in their orbits, but most of the time Sirius is brighter than both of them. Among the actual stars, nothing comes close. The second brightest star in the sky is called Canopus, and Sirius is almost twice as bright as that. So why is it so bright? There are really two reasons, and both of them matter. The first reason is that Sirius is a genuinely luminous star. It puts out about 25 times more light than our Sun. Its surface is much hotter, roughly 10,000 degrees on the Kelvin scale, compared to about 5,800 for the Sun. That higher temperature means it radiates more energy per unit of surface area, and its surface area is already larger. Sirius has about 1.7 times the radius of the Sun and about twice the mass. So it is a bigger, hotter, more powerful star than the one we orbit, but it is not an extreme star. There are stars in the galaxy that are hundreds of thousands of times more luminous than the Sun. Compared to those, Sirius is fairly modest. The reason it looks so bright to us is the second factor. Sirius is close. In astronomical terms, it is practically next door. It sits about 8.6 light-years from Earth. A light-year is the distance that light travels in 1 year, moving at about 186,000 miles per second. So the light you see when you look at Sirius left that star roughly 8.5 years ago. That is not very long. Compare that to a star like Rigel in the constellation Orion, which is about 860 light-years away. Rigel is far more luminous than Sirius in absolute terms, maybe 70,000 times brighter than the Sun. But because it is so much farther away, it appears dimmer in our sky. Sirius, at only 8.6 light-years, is one of the very closest star systems to us. It is the fifth nearest stellar system overall, just about twice as far as Alpha Centauri, which is the closest star system beyond our own Sun. So the brightness of Sirius comes from a combination. It is a star that is genuinely brighter than average, and it happens to be very nearby. Neither fact alone would make it the brightest star in our sky. There are closer stars that are much dimmer. There are more luminous stars that are much farther away. Sirius sits in a kind of sweet spot, and that is why it dominates the night. Finding Sirius is not difficult. If you can find Orion, you can find Sirius. Orion is one of the most recognizable patterns in the sky, largely because of the 3 stars that form a short, straight line in the middle of the constellation. Those 3 stars are called Orion's belt. If you draw an imaginary line through the belt and extend it downward and to the left, from the perspective of someone in the northern hemisphere, that line points almost directly at Sirius. The distance from the belt to Sirius is roughly 8 times the width of the belt itself. You cannot miss it. It is the brightest thing in that part of the sky, and there is nothing nearby that could be confused with it. From most of the United States and similar latitudes, Sirius rises in the southeast, sweeps across the southern sky, and sets in the southwest. It is best seen during the winter months. By December, it rises in the mid-evening. Through January and February, it is high and prominent. By April, it is already sinking into the southwest after dark. From the southern hemisphere, Sirius climbs much higher overhead and is visible during their summer evenings. Sirius is also part of a pattern called the Winter Triangle, which is formed by three bright stars: Sirius, Betelgeuse in Orion, and Procyon in Canis Minor. These three are among the brightest in the winter sky, and they form a large, obvious triangle that is easy to spot once you know to look for it. One thing people often notice about Sirius, especially when it is low in the sky, is that it seems to flash different colors. It can look red for a moment, then blue, then green, then white. The effect can be startling. Some people see it and think they are looking at an aircraft. Others have reported it as a UFO. But what is actually happening is straightforward, and it has nothing to do with the star itself. All stars twinkle. Astronomers call this scintillation. It happens because starlight has to pass through the Earth's atmosphere before it reaches your eyes, and the atmosphere is not still. It is made up of layers of air at different temperatures and densities, all of them moving and shifting constantly. These moving pockets of air bend the light slightly, changing its direction by tiny amounts, many times per second. The result is that the star appears to flicker. But Sirius is special in this regard for two reasons. First, it is very bright, which means the flickering is much more noticeable to the eye. A dim star might twinkle just as much, but you would not see the effect as clearly. Second, from northern latitudes, Sirius is often viewed when it is fairly low on the horizon. When a star is low, its light is passing through a much thicker slice of the atmosphere compared to a star directly overhead. More atmosphere means more turbulence, more bending, and more dramatic twinkling. The atmosphere does not just make the star flicker in brightness, it also acts like thousands of tiny prisms, splitting the star's white light into its component colors. At any given instant, a slightly different color might be bent toward your eyes. So instead of a steady white point of light, you see rapid flashes of red, blue, green, and white, all happening very quickly. The effect is genuine. It is physics, and it only happens because we are looking through a blanket of moving air. If you could stand on the surface of the moon, where there is no atmosphere, Sirius would appear as a perfectly steady, unblinking white point. The Hubble Space Telescope, which orbits above the atmosphere, sees stars exactly that way. No twinkling at all. When Sirius is higher in the sky, the twinkling calms down. There is less air between you and the star, so there is less distortion. If you watch Sirius over the course of an evening, rising from the southeast and climbing toward the south, you can actually see this happen. Near the horizon, it sparkles with color. Higher up, it settles into a steadier, whiter glow. Now Sirius looks like a single point of light, but it is not a single star. It is two stars orbiting each other. The bright one, the one we see, is called Sirius A. Its companion, much smaller and much fainter, is called Sirius B. You cannot see Sirius B with the naked eye. You cannot even see it easily with a telescope, because it is so close to Sirius A and so much dimmer that it gets lost in the glare. But it is there, and its discovery was one of the more interesting stories in the history of astronomy. In 1844, a German astronomer named Friedrich Wilhelm Bessel was studying the motion of Sirius very carefully. He was measuring its position in the sky over time, watching how it moved relative to other stars. Stars do move, they are not fixed, but their motions are so slow, from our perspective, that it takes precise measurements over years to detect them. What Bessel noticed was that Sirius was not moving in a straight line. It was wobbling. Its path had a slight back and forth wiggle to it, as if something unseen was pulling on it gravitationally. Bessel concluded that Sirius must have a companion, another star orbiting with it, whose gravity was causing the wobble. He estimated that the two stars completed one orbit around each other in about 50 years. This was a bold claim because nobody could see the companion. For nearly 20 years, astronomers looked for it without success. Then in 1862, an American telescope maker named Alvin Graham Clark was testing a new lens he had just built. He pointed the telescope at Sirius, and there, very close to the bright star and very faint, was a tiny point of light. Bessel's companion existed. It was real, and it was given the name Sirius B. But the real surprise came later. In 1915, an astronomer named Walter Adams at the Mount Wilson Observatory managed to study the light coming from Sirius B in detail. He examined its spectrum, the specific pattern of colors in its light, which tells astronomers about a star's temperature and composition. What he found was strange. Sirius B was extremely hot. Its surface temperature was around 25,000 degrees Kelvin, much hotter than Sirius A's 10,000. And yet it was incredibly dim, about 10,000 times fainter than Sirius A. That combination does not normally happen. A hot star should be bright. The only way a star can be very hot and very faint at the same time is if it is very small. When astronomers worked out the math, they realized that Sirius B had to be roughly the size of the Earth, maybe about 12,000 kilometers across, but it contained about the same amount of mass as our entire Sun. The density was almost unimaginable. A teaspoon of material from Sirius B would weigh somewhere between 5 and 15 tons on Earth. Nobody had seen anything like this before. The idea of a star the size of a planet, but the weight of the Sun was so unusual that it took physicists years to explain it. The explanation eventually came from quantum mechanics, the branch of physics that describes how matter behaves at the atomic level. In the early 1930s, a young Indian physicist named Subrahmanyan Chandrasekhar worked out the theory while on a ship traveling to England. He showed that when a star runs out of fuel and collapses, the electrons in its matter can be packed so tightly that they resist further compression through a quantum mechanical effect called degeneracy pressure. This pressure holds the star up against gravity, even though no nuclear reactions are happening anymore. The result is a white dwarf, a dead star, still glowing from residual heat, but no longer generating new energy. Sirius B was one of the very first white dwarfs ever identified, and its discovery helped open an entirely new area of astrophysics. Understanding what white dwarfs are and how they form turned out to be essential for understanding the life cycles of most stars in the galaxy. More than 97% of all stars in the Milky Way will eventually end their lives as white dwarfs. Our own Sun will become one in about 5 billion years. The story of how Sirius B reached its current state is worth understanding because it tells us something about how stars age. The Sirius system is estimated to be about 225 to 250 million years old. That is young as stars go. Our Sun is roughly 20 times older, but Sirius B has already gone through its entire life cycle and died. That is because Sirius B was once a much larger star. When it was on the main sequence, meaning when it was actively burning hydrogen fuel in its core, it was probably about 5 times more massive than the Sun. Stars with more mass burn their fuel faster. They are hotter, brighter, and they run out of hydrogen much more quickly. A star 5 times the Sun's mass might only last about 100 million years on the main sequence, compared to about 10 billion years for the Sun. After roughly 100 million years, Sirius B exhausted the hydrogen in its core. When that happens, a star undergoes a dramatic change. The core contracts while the outer layers expand enormously. The star swells up and becomes what is called a red giant. If Sirius B went through a red giant phase, it would have become vastly larger than it was before, possibly large enough that its outer layers came close to Sirius A. Eventually, the red giant shed its outer layers. The gas was released into space, and what remained was the hot, dense core. That core is what we now see as Sirius B. This happened about 120 million years ago. Since then, Sirius B has just been sitting there, slowly cooling. It has no fuel left to burn. It generates no new energy. The heat it still has is left over from its earlier life, and it is radiating that heat away into space very gradually. Over billions of years, it will get dimmer and cooler, eventually fading to the point where it emits almost no light at all. The two stars orbit each other with a period of about 50 years, which is close to what Bessel originally estimated. Their average separation is about 20 astronomical units. An astronomical unit is the distance from the Earth to the Sun, so 20 astronomical units is roughly the distance from the Sun to the planet Uranus. But the orbit is not circular. It is an ellipse, and a fairly stretched out one. At their closest approach, Sirius A and B are only about 8.2 astronomical units apart. At their farthest, they are about 31.5 astronomical units apart. The last time they were closest was in 1994. They reached their maximum separation in 2019. From Earth's point of view, the widest apparent gap between them happened in 2023. This matters for anyone trying to observe Sirius B through a telescope, because when the two stars are close together in the sky, the glare from Sirius A makes it almost impossible to see its tiny companion. You generally need a telescope with at least a 12-inch mirror, good atmospheric conditions, and the stars need to be far enough apart in their orbit. There have been observations since the late 1800s suggesting there might be a third star in the system, sometimes called Sirius. The idea is based on small irregularities in the orbit that could be explained by the gravitational pull of something else. If it exists, it would be very small, perhaps a low-mass red dwarf or a brown dwarf, orbiting Sirius A every 6 years or so, but no one has ever directly detected it. Observations with the Hubble Space Telescope in 2017 ruled out any companion with a mass large enough to be a normal star. The question is still technically open for very small objects, but most astronomers consider it unlikely. Sirius A itself still has a long life ahead of it, though not as long as the Sun's. It is estimated that within about 1 billion years from its formation, Sirius A will use up the hydrogen in its core. When that happens, it will follow a similar path to the one Sirius B already took. It will expand into a red giant, eventually shed its outer layers, and collapse down into a white dwarf. At that point, the Sirius system will consist of 2 white dwarfs orbiting each other, both slowly cooling, both gradually dimming over billions of years. But for now, Sirius A is still in the prime of its life, and it is moving toward us, not quickly in human terms, but steadily. The Sirius system is gradually getting closer to our solar system, and because of that, it will appear very slightly brighter over the coming tens of thousands of years. It will reach a peak brightness in about 60,000 years. After that, its distance will start to increase again, and it will slowly fade. But it will remain the brightest star in Earth's night sky for roughly the next 210,000 years. After that, the title will pass to Vega, another bright star, which is intrinsically more luminous and will eventually be better positioned relative to our solar system. There is another curious thing that will happen in the distant future. Around the year 66,270 AD, because of a slow wobble in Earth's rotational axis called axial precession, combined with the motion of Sirius through space, the star will pass very close to the south celestial pole. For a brief period in astronomical terms, Sirius will nearly be the southern pole star. It will come within about 1.6 degrees of the pole, which is remarkably close. Then it will move away again. None of this will be perceptible to anyone alive now. These are changes that unfold over thousands and tens of thousands of years, but they are real and they are predictable, and they give a sense of how the sky is not fixed. It is always changing, just very slowly. The idea of stars moving through space can feel counterintuitive because the night sky looks so permanent. The constellations appear tonight almost exactly as they appeared last year and last century and 1,000 years ago. But that appearance of permanence is an illusion created by distance. The stars are all moving, some very fast. But they are so far away that their motions are barely detectable over a human lifetime. Over thousands of years, though, the changes add up. If you could watch the sky in fast forward, the constellations would gradually distort, stretch, and eventually become unrecognizable. Sirius, being one of the closest stars, actually moves faster across the sky than most. It has a relatively high proper motion, which is the term astronomers use for a star's apparent movement against the background of more distant stars. Bessel's ability to detect the wobble in that motion, back in 1844, was partly because Sirius moves enough that precise measurements could pick up the subtle variation. For a more distant star, the same wobble would have been too small to notice. That method of detecting unseen companions through gravitational wobble, which Bessel pioneered with Sirius, turned out to be tremendously important. A version of the same technique is used today to discover planets around other stars. When a planet orbits a star, its gravity pulls the star very slightly, causing a tiny back-and-forth motion. Astronomers can detect this motion through precise measurements of the star's position or through shifts in its light spectrum. Hundreds of exoplanets have been found this way. The basic principle goes back to Bessel and Sirius. Sirius B itself contributed to another area of physics. Because white dwarfs are so dense, they have very strong gravitational fields for their size. Einstein's general theory of relativity predicts that light escaping from a strong gravitational field should be shifted toward the red end of the spectrum, an effect called gravitational redshift. Sirius B's gravitational redshift was measured and confirmed, providing one of the early observational tests of general relativity. The Sirius system, in this way, has been a kind of natural laboratory. Its proximity, its brightness, and the fact that it contains both a normal star and a white dwarf have made it useful for testing a range of physical theories. The Egyptians had no way of knowing any of this. They did not know that Sirius was a binary star, or that one of its components was a dead stellar core the size of the Earth. They did not know its distance, or its temperature, or its mass. What they knew was that it was the brightest star, and that it appeared in the sky at a very specific and very reliable time each year. In ancient Egypt, Sirius was called Sothis. That name came from the Egyptian word Soptit. The Egyptians watched for the moment when Sirius first became visible in the eastern sky just before sunrise, after a period of weeks during which it had been hidden by the sun's glare. This event is called a heliacal rising. For Sirius, it happened with remarkable regularity, returning to the same position relative to the sunrise almost exactly every 365 1/4 days. That is very close to the actual length of a year, and the Egyptians recognized this. The heliacal rising of Sirius happened to coincide with the annual flooding of the Nile River. The Nile flood was the most important event in the Egyptian agricultural calendar. It brought water and fresh silt to the farmland along the river, making the soil fertile for the coming growing season. Without the flood, the crops would fail. With it, Egypt prospered. The appearance of Sirius in the pre-dawn sky became a signal that the flood was coming. The Egyptians celebrated this with a festival called the Coming of Soptit, and they used it to mark the beginning of their new year. Over time, the Egyptians associated Sirius with the goddess Isis. The nearby constellation of Orion was connected to Osiris, the husband of Isis in Egyptian mythology. The 70-day period each year when Sirius was absent from the sky, hidden by the sun, was understood as a time when Isis and Osiris were passing through the underworld. When Sirius reappeared, it was a kind of return, a renewal. Some Egyptian temples were built with their orientations aligned to the point on the horizon where Sirius would rise. The star was central to their religious and civic life, not because of any mystical property, but because of that extraordinary reliability. It appeared at the same time each year, and it predicted the flood. In a civilization that depended entirely on the Nile, that made it the most important star in the sky. There is one persistent mystery related to Sirius and the ancient world. Around the year 150 AD, the astronomer Claudius Ptolemy, working in Alexandria, compiled a catalogue of stars. He described Sirius as reddish in color. This is odd, because Sirius today is unmistakably white or blue-white. Ptolemy also listed 5 other stars as red, including Betelgeuse, Antares, and Arcturus, all of which are genuinely red or orange today. So his descriptions were generally accurate, but Sirius is not red. Various explanations have been proposed. One possibility is that Ptolemy was describing Sirius as seen near the horizon, where atmospheric effects can make any star appear reddish, much the same way the sun looks red at sunrise and sunset. Another possibility involves Sirius B. Some researchers have speculated that when Sirius B was in its red giant phase, it might have been the more visually prominent star in the system, making the pair appear red. But the timeline does not work well for this. Sirius B became a white dwarf roughly 120 million years ago, long before any human observer could have seen it as a red giant. The red Sirius question remains open, with no fully satisfying answer. The Egyptian calendar system was closely tied to the Sothic cycle. The alignment between the heliacal rising of Sirius and the civil calendar created what modern scholars call the Sothic cycle, a period of about 1,461 years over which the Egyptian calendar, which did not account for the extra quarter day per year, would slowly drift out of alignment with the star and then come back into alignment again. Greeks had a very different relationship with Sirius. They associated its appearance with the peak of summer heat, and they blamed the star for it. The logic, by their understanding, was that the combined heat of the sun and the brightest star must be what made the hottest days so unbearable. They called this period the dog days after the dog star, and they considered it an ominous time. Plants wilted, people felt weak, dogs panted and in the worst cases went mad with what might have been rabies. The Romans used the Latin term dies caniculae for these same days, from canicula, meaning little dog. Homer mentions Sirius in the Iliad. He described the star rising in late summer, brilliant and unmistakable, and associated it with both beauty and danger. The poet Tennyson, much later, wrote about how Sirius seemed to change color as it flickered, shifting between red and emerald, which is a very accurate description of the scintillation effect caused by the atmosphere. Far from the Mediterranean, other cultures noticed Sirius independently and built their own meanings around it. For the Polynesians, scattered across thousands of islands in the Pacific, Sirius marked the beginning of winter in the southern hemisphere. More practically, it was a navigational star. Polynesian sailors used Sirius and other bright stars as reference points when crossing open ocean in canoes, without compasses or charts. The star's fixed position relative to the horizon at certain times of year made it a reliable marker for direction. In ancient China, Sirius was imagined as a heavenly wolf. A large celestial pattern resembling a bow and arrow was seen stretching across the southern sky, with the arrow tip pointed at the wolf. In the Indian Vedas, the star was called the chieftain's star. In other Hindu writings, it was referred to as Sukra, the rain star. In ancient Chaldea, the region that is now Iraq, it was called the dog star that leads. The pattern of associating Sirius with a dog or wolf appears across many cultures that had no contact with each other. This is probably not a coincidence, but it is also not mysterious. The most likely explanation is simple observation. Orion is one of the most recognizable figures in the sky, a large pattern that looks convincingly like a standing or walking human figure. Sirius follows behind Orion as both rise and cross the sky. A bright point of light following a human figure across the heavens looks like a dog following its master. Multiple cultures, watching the same sky, arrived at the same interpretation independently. One of the more debated cultural connections involves the Dogon people of Mali in West Africa. In the 1930s, two French anthropologists, Marcel Graillul and Germain Dieterlen, spent time with the Dogon and later reported that Dogon traditions contained knowledge about the Sirius system that seemed impossible to obtain without a telescope. Specifically, they said the Dogon knew that Sirius had a companion star, that the companion was small and extraordinarily dense, and that the two stars orbited each other over a period of about 50 years. This claim attracted a great deal of attention when the author Robert Temple published a book about it in 1976. Temple proposed that the Dogon might have received this knowledge from contact with an intelligent species from the Sirius system in the distant past. The idea was dramatic, and it generated lasting public interest. But the scholarly response has been largely skeptical. In 1991, the anthropologist Walter van Beek went back to the Dogon and conducted his own research. He found that the Dogon themselves did not agree on which star their traditions referred to. Some said it was an invisible star, some said it was Venus. Their accounts were not consistent in the way Graillul's report had suggested. Other researchers pointed out that a French astronomical expedition had visited central West Africa in 1893 to observe a total solar eclipse, and that European missionaries and travelers had been in the region for decades before Graillul arrived. The possibility that the Dogon's astronomical knowledge came from relatively recent contact with Europeans, rather than from ancient or extraterrestrial sources, is considered much more likely by most scholars. Carl Sagan made this argument as well. The Dogon traditions are real and culturally rich, but the specific claims about advanced pre-telescopic knowledge of Sirius B remain unconfirmed and contested. What is not contested is the role Sirius has played across civilizations as a fixed point in the sky, a marker of seasons, a trigger for calendars, and a source of stories. It is one of the few stars that most people can name, and it is among the easiest to find. Its brightness is part of why it has held such a prominent place in human attention for thousands of years. There is a concept in astronomy that is useful for understanding why some stars appear brighter than others, and Sirius is a good example for illustrating it. The concept involves the difference between apparent magnitude and absolute magnitude. Apparent magnitude measures how bright a star looks from Earth. It is what your eyes perceive. Absolute magnitude measures how bright a star actually is, independent of distance, as if every star were placed at a standard distance of about 32.6 light-years from the observer. Sirius has an apparent magnitude of -1.46. On this scale, lower numbers mean brighter objects. The Sun has an apparent magnitude of about -26.7, which makes sense because it is so close. The full moon is about -12.7. Venus at its brightest is about -4.6. Sirius, at -1.46, is brighter than any other star, but dimmer than these much closer objects. Its absolute magnitude, though, is about +1.4. That means if you moved Sirius out to the standard distance of 32.6 light-years, it would still be a noticeable star, but it would not be particularly outstanding. There are many stars with lower absolute magnitudes, meaning they are more inherently luminous. Rigel, for example, has an absolute magnitude of about -7, making it enormously more powerful than Sirius in absolute terms. But Rigel is about 860 light-years away, so it appears fainter in our sky. This distinction between how bright something looks and how bright it actually is turns up in all sorts of places, not just astronomy, but in the case of Sirius, it explains a sometimes confusing point. Sirius is the brightest star we can see, but it is not the most luminous star in the galaxy, not even close. It just happens to be a reasonably bright star that is very nearby. The magnitude system itself has a long history. It goes back to the ancient Greek astronomer Hipparchus, who in the 2nd century BC ranked the stars he could see into 6 categories based on brightness. The brightest stars were 1st magnitude. The faintest he could see was 6th magnitude. Much later, when astronomers made this system more precise, they found that a difference of 5 magnitudes corresponds to a factor of exactly 100 in brightness. So a 1st magnitude star is 100 times brighter than a 6th magnitude star. The scale was eventually extended in both directions. Objects brighter than 1st magnitude were given 0 or negative numbers. Sirius, at -1.46, sits at the extreme bright end of the stellar scale. The faintest objects detectable by modern telescopes have magnitudes of around +30 or higher, which makes them billions of times fainter than what the unaided eye can see. Light that arrives at Earth from Sirius tonight left the star about 8.5 years ago. That means when you look at Sirius, you are seeing it as it was in the past, not as it is right now. This is true of everything you look at, technically. Light from the lamp across the room took a tiny fraction of a second to reach your eyes. Light from the moon took about 1.3 seconds. Light from the sun took about 8 minutes. But for most everyday objects, the delay is so small it does not matter. For stars, the delay is measured in years, and for distant galaxies, in millions or billions of years. In the case of Sirius, 8.5 years is not very long. The star is not going to change appreciably in that time. But the principle is important because it means that looking at the sky is always looking at the past. The farther away something is, the older the light. When astronomers study galaxies billions of light years away, they are seeing those galaxies as they were billions of years ago, when the universe was much younger. Sirius, being nearby, gives us a very recent picture. Almost real time by astronomical standards. The Sirius system is about 225 to 250 million years old. To put that in context, that is roughly the beginning of the Triassic period on Earth, the time when dinosaurs were first appearing. The Sun, by contrast, is about 4.6 billion years old. Sirius is a young system. And yet, in that relatively short time, one of its stars has already been born, lived its full life, expanded into a red giant, shed its outer layers, and collapsed into a white dwarf. The reason for this, again, is mass. Sirius B started out much more massive than Sirius A, and massive stars evolve much faster. This is one of the counterintuitive things about stellar physics. You might expect that a star with more fuel would last longer, but the opposite is true. A more massive star has more hydrogen, yes, but it also has much higher temperatures and pressures in its core, which cause it to burn through that fuel at a much faster rate. A star 10 times the mass of the Sun might have 10 times as much fuel, but burn it 1,000 times faster, resulting in a lifespan 100 times shorter. The Sun will last about 10 billion years. A star with 10 solar masses might last only 10 to 20 million years. The math is not proportional. The more massive the star, the more dramatically shortened its life. Sirius A, at about 2 solar masses, will have a lifespan on the main sequence of roughly 1 billion years. That is much shorter than the Sun's, but much longer than Sirius B's original lifespan, which was only about 100 million years. When Sirius A eventually does run out of hydrogen, it will not explode. Stars of its mass do not end in supernovae. That fate is reserved for stars roughly 8 times more massive than the Sun or greater. Instead, Sirius A will go through the same process Sirius B went through. It will expand into a red giant. It will shed its outer layers, possibly forming a planetary nebula, a shell of glowing gas expanding outward, and the core will remain behind as a new white dwarf. At that point, many hundreds of millions of years from now, the Sirius system will be a pair of white dwarfs, both small, both dense, both slowly losing heat. The system will still be gravitationally bound, the two remnants orbiting their common center of mass, but there will be no starlight to speak of. Both objects will be dimming, year by year, over timescales that dwarf the current age of the universe. White dwarfs cool very slowly. Their small size means they have a relatively small surface area through which to radiate heat, and they start out very hot. Sirius B, for example, still has a surface temperature of about 25,000 Kelvin, more than 100 million years after it stopped generating energy. The cooling process will continue for billions of years. The temperature drops faster at first, when the star is hottest, and then the rate of cooling slows as the star gets dimmer and cooler. The physics of this process is well understood and can be modeled with precision. Astronomers use white dwarf cooling models as a kind of clock. Because the temperature of a white dwarf tells you approximately how long ago it stopped being a normal star. Eventually, in theory, a white dwarf would cool to the point where it emits essentially no light or heat at all, becoming what is sometimes called a black dwarf. But the universe is only about 13.8 billion years old, and the cooling time required is longer than that. No black dwarfs exist yet anywhere. The universe is simply not old enough. Every white dwarf that has ever formed is still warm enough to glow, at least faintly. This includes white dwarfs that formed in the earliest generations of stars billions of years ago. They are dim, certainly. Some are among the faintest objects in the galaxy, but none have gone fully dark. Sirius B, then, is a star in the very early stages of an incomprehensibly long cooling process. It will still be warm, in relative terms, long after the Sun itself has exhausted its fuel and become a white dwarf of its own. There is something interesting about what the Sun would look like from the Sirius system. If you could stand on a planet orbiting Sirius A, which as far as we know does not exist, and look back toward our solar system, the Sun would appear as a faint star. It would be roughly a second magnitude star, meaning it would be visible to the naked eye, but not particularly remarkable. It would be one of many faint points of light in the background. You would not single it out as anything special. The idea that our entire world, our entire civilization, everything that has ever happened on Earth, is attached to that unremarkable dot is the kind of thought that simply sits there without requiring a response. From the Sirius system, the familiar constellations of our sky would look nearly the same. Most stars are so far away that shifting your viewpoint by 8.6 light-years does not significantly change their apparent positions. The Big Dipper would still look like the Big Dipper. Orion would still be recognizable. The main difference would be the addition of the Sun as a new star in the field, visible but easy to overlook. The Hubble Space Telescope has taken several images of the Sirius system. In one well-known photograph, Sirius A is deliberately overexposed, blown out into a large bright spot with diffraction spikes radiating outward, so that the faint Sirius B can be seen as a tiny dot nearby. The cross-shaped spikes and concentric rings around Sirius A in the image are artifacts of the telescope's optics, not real features of the star. They are what happens when an extremely bright point source of light passes through a telescope's internal structure. Sirius B, in the same image, appears as a small, unremarkable dot, with a faint ring around it. That small dot contains a mass equal to the Sun's, compressed into a volume the size of the Earth. The image is quiet and undramatic, which is appropriate because the universe does not generally announce its extremes. The Chandra X-ray Observatory has also studied the Sirius system. Sirius B, despite being so faint in visible light, is a stronger source of X-rays than Sirius A. This is because its surface is much hotter, and at those temperatures, a significant fraction of the energy is emitted as X-ray radiation rather than visible light. For human eyes, Sirius B is almost invisible. For an X-ray telescope, it is the brighter of the two. Observations of Sirius continue to contribute to science. The precise measurement of Sirius B's mass, radius, and temperature has been used to test the mass-radius relationship for white dwarfs, a theoretical prediction that more massive white dwarfs are actually smaller in radius due to greater gravitational compression. Sirius B, with its well-known mass and close proximity to Earth, is one of the best available test cases for this relationship, and it has confirmed theoretical predictions with high accuracy. The gravitational redshift of Sirius B has also been measured using the Hubble Space Telescope spectrograph. Light escaping from the surface of Sirius B is stretched slightly toward longer wavelengths because of the white dwarf's intense gravity. The degree of stretching matches what general relativity predicts for an object of that mass and size. It is not a dramatic test, in the sense that general relativity has been confirmed by many other observations. But it is a clean, local measurement, and it adds to the overall confidence in the theory. It is worth noting what Sirius is not. It is not the closest star to Earth. That is Proxima Centauri, part of the Alpha Centauri system, at about 4.2 light-years. It is not the most luminous star in the sky in absolute terms. That title, among visible stars, goes to candidates like Rigel or Deneb or other blue supergiants. It is not the largest star. Red supergiants like Betelgeuse or UY Scuti dwarf it in physical size. It is not the hottest star. There are stars with surface temperatures exceeding 100,000 Kelvin. What Sirius is, specifically and precisely, is the brightest star in Earth's sky, and it achieves that by being a reasonably luminous star at a very short distance. There is a kind of modesty in that. The brightest star in the sky is not a supergiant or a rare exotic. It is a fairly ordinary main-sequence star, about twice the mass of the Sun, a little hotter, a little bigger, a little younger. It just happens to be nearby. The universe is full of objects far more extreme than Sirius, but most of them are too far away to be noticed by anyone looking up without a telescope. Sirius is visible from nearly everywhere on Earth. The only places it cannot be seen are above about 73 degrees north latitude, deep inside the Arctic. From everywhere else on the planet, at the right time of year and the right time of night, it can be found. This near-universal visibility is part of why so many different cultures, across so many different continents and millennia, develop traditions and stories about it. It is one of the very few celestial objects that the entire world shares. The system has been where it is, relative to us, for long enough that many generations of many civilizations have known it, and it will stay bright, stay dominant, stay recognizable for more generations than anyone can reasonably count. 210,000 years is a long time. Modern humans have existed for roughly 300,000 years. So Sirius has been the brightest star for most of the time our species has existed, and it will continue to be for a span nearly as long as all of recorded history many times over. When it eventually fades from the top of the list, the change will not be sudden. It will not be a single moment where the torch passes. Sirius will slowly dim over tens of thousands of years as it moves away, and Vega will slowly appear to gain on it. There may not be a single century where anyone alive would notice the difference. The change is real, but it is so gradual that it exists only in the aggregate, visible only from the perspective of deep time. For now and for a very long time to come, Sirius holds its position. It rises in winter evenings from the northern hemisphere. It follows Orion. It twinkles through the atmosphere in colors that are not its own. It carries a dead companion star that once outshone it, packed into a space no larger than the world we live on. It has been called the Dog Star, the Nile Star, the Scorcher, and the Chieftain's Star. Temples were built facing it. Calendars were anchored to it, sailors steered by it. And none of that changes what it is, which is a hot, white, moderately massive star about 8.5 light-years away, burning hydrogen in its core, circled by the remnant of a star that went through the same process faster and finished first. It is there now, if it is the right time of year and the sky is clear, the same point of light the Egyptians watched for, the same one the Greeks blamed for summer, the same one Friedrich Bessel stared at so carefully that he could detect the wobble of an invisible companion, the same light from the same star, arriving after the same 8.5-year journey. The constellation shifts slowly westward as the weeks pass. In December, Sirius rises in the early evening. In February, it stands at its highest. By April, it is already sinking. By summer, it is gone from the evening sky, hidden behind the sun, and the Egyptians would have begun counting the days until it reappeared. That cycle continues. The star rises and sets with the turning of the year, the way it has for as long as anyone has been watching, which is as long as there have been people to watch. The heliacal rising of Sirius still happens at roughly the same interval, 365.25 days, which is as close to the length of a year as a star can manage. The Nile no longer floods the way it once did, because modern dams control its flow, but the star still rises. The timing is unchanged. The light arriving tonight is about 8.5 years old. The star itself is about 250 million years old. The white dwarf beside it stopped producing energy over 100 million years ago and is still warm. The system will continue to shine for hundreds of millions of years longer, and for the next 200,000 or so, it will remain the brightest star that anyone on Earth can see. There is not much else to say about that. It is just a star doing what stars do, but it is the brightest one, and it has been for a very long time, and it will be for a while longer.